One. Um, it's always cold in this room. It gives me great pleasure to welcome our colloquium speaker today, James Analytis. James is currently the Charles Cattell Chair in Condensed Matter Physics at Berkeley. He's originally from New Zealand. He got his DPhil at Oxford in 2006, and after some time at Bristol and at Stanford, he joined the Berkeley faculty in 2013. He was chair of the physics department at Berkeley from 2020 to earlier this year. And he is an expert in material synthesis as well as novel characterization techniques for all kinds of interesting quantum materials. And he's working on some of the, I could list all of his awards. He has won many. He is working on some of the hottest material systems in condensed matter physics today. And he's going to tell us today about the boundaries of equilibrium.
Thanks, Doug. Thank you for that introduction. It's a real pleasure to be here and visit Rice. Today I'm going to tell you a story that's really about a journey in condensed matter physics, and it's obviously biased by my own journey. So let me start by asking a simple question: what is condensed matter physics? And often giving broad talks. Is this a bit too loud? It feels like it might be. Oh, I guess that's right. Often giving talks about condensed matter physics can be, at least popular talks, can sometimes be a bit challenging because we don't really work on typically the problems that at least the public generally associate with when they think of what a physicist does. Because we're not really at the smaller scale, where you ask the question, what are the fundamental particles? What is dark matter? What is the essence of the material universe? And we're also not at the cosmological scale, where you might be asking questions about the nature of gravity waves, or whether quantum mechanics is commensurate with gravity questions, or black holes, or those kinds of things. We're really at all the scales in between, the intermediate scales. And, well, as Doug said, I spent a little bit of time in Bristol. And, my mentor at the time, who felt like he needed to give me advice about lots of things outside of physics as well, once said that, if I'm ever on a romantic walk on a beach, one neat thing to say is that, did you know that in this grain of sand, there are more atoms than there are stars in the universe? As it turns out, that didn't really work very well. But one thing that did turn out to work for me is that when my girlfriend at the time, now my wife, thought for the first few years that we were dating that I studied condensed matter physics. If anyone doesn't know why that is, you just have to listen to my accent for a little bit. So I think it got my foot in the door that I was in this bizarre subject in philosophy for the longest time. But no. I'm in condensed matter physics. And what you see here is really a picture of a grain of salt, which is not exactly the metaphor that I'm looking for when I'm trying to explain how important condensed matter physics is to the world. But what we do is that, especially in my research area, is that we look for exotic emergent excitations in the system, exotic new particles that might not even exist in the standard model. Or might be particles that we're still looking for that might come out of the standard model. Things like fractional excitations, or anyons, or axions, chiral fermions, Majoranas. You can see that, to some degree, condensed matter physicists have some degree of envy of high energy physicists. So a lot of the things that we look for turn out to have the same names of things that they've already studied. But that's the kind of thing that happens in a material which really is composed of the simplest things that we do understand very well: atoms and electrons. But what happens is that when you have lots of electrons in one place, is that they interact. And those interactions are what lead to some of the most interesting phenomena in condensed matter physics. So it's frankly the many-body problem, and interactions are at the core of it. And that's really what we study as condensed matter physicists. It's the physics of interacting systems. Okay. A gas is an example of a many-body system that isn't interacting. The whole idea, so you can think of, it's a many-body system in some sense, but it's actually really many single bodies. And that's because each particle in a gas basically behaves like a little island, isolated from all the other ones, so it's independent. So even though it's a many-body problem, it's really many single-body problems. And I know a lot about islands because, as Doug said, I'm from one. And there are 3 facts that usually people come to me with about New Zealand. 1, do I know the Flight of the Conchords? No? No. The second one is the Lord of the Rings. And the third one is, are there really more sheep than people in New Zealand? There are an order of magnitude more sheep than people in New Zealand, if you want to know. And that leads me to this picture of flocking sheep. It's not a great video on the scale. It works better on a smaller scale. But what you're supposed to see is basically flocking sheep as they move through a series of bushes. And what you see is that it looks like at some points these sheep really start to flow. And that flow, as they cluster together, this really isn't working in quite the same frame by frame. Let me just pause it so you can, let me see it there. Okay. You can see in this frame that at any one point, especially in this channel right here, when you look at one of the sheep, all the sheep around it are doing exactly the same thing. Why are they doing the same thing? It's because there's an interaction that's happening between them, right? There's an idea that even though they're independent bodies, they have a collective behavior that comes together when they start flocking. Okay. All right. And that brings me to the idea of order and broken symmetry. One of the central things that we think about as condensed matter physicists when particles interact is what happens to them when they are behaving in this collective way, when they are seeing each other and working together to give a new kind of behavior that isn't purely understood from just understanding the single particle by itself. Okay, so what is order? Imagine you're a sheep, and what you're doing is that you're looking at the behavior at all the sheep around you. And what you're doing is you're mimicking all of that behavior because there's some interaction that makes you want to do that, whatever that is. They want to go in the same direction, or they want self-protection, or whatever. That's the basic idea between interactions of fundamental particles in a solid as well. So when you think of a ferromagnet, what we think of is spins that exist on electrons, which we're all familiar with in quantum mechanics. But they see each other, they're interacting, and they're interacting in such a way that they all want to point in the same direction. So just as sheep are now following each other, each spin is following its neighbors. And those correlations are really the essence of what happens when you have an interacting system. By the way, I should say, feel free to interrupt me at any point, especially if I say something really wrong. There's another kind of interaction called an antiferromagnetic interaction, which people are less familiar with. And that's when a spin sees its neighbors, but it wants to do exactly the opposite of its neighbors, right? And then the spins are basically always anti-aligned if you go in any direction along its nearest neighbors. Okay. I wasn't sure what to call the first one, but I call it a sheep crystal. All right. But the essence of, I guess, the concept there is really one of what we call broken symmetry. So let me tell you a bit about that. So in particular, when we talk about the sheep crystal, any kind of crystal, that's really composed of things that we understand, atoms and electrons, that at one stage, at some high temperature, were all a gas, and then as we cooled the temperature down, they saw each other and started to interact, and they formed a crystal. When they were a gas, what we say is that they're translationally invariant. If you look at any one point in the gas, one particle, it behaves just the same as any of the other ones, and all of its neighbors are exactly doing, are as independent as each other. That's a translationally invariant system, and what I'm showing here is basically a pixelated picture of what they would look like. So let's say we're looking at these pixels represent spins. White might represent upspin, and black might represent downspin. if you go to any point on this picture, you're just as likely to be near an upspin as you are a downspin. That's what translational invariance looks like on the scale. When you have order, or when you have interactions and those spins start to see each other, that's when you have broken translational invariance. And now if you go to any point on this pixelated plot, you're now more, if you're an upspin, you're more likely to be near other upspins. If you're a downspin, you're more likely to be near other downspins. And that is now where you're not a translationally invariant system anymore. And there's some idea of when you actually zoom out, you can actually see what the order might look like. All right. Okay. There's going to be more sheep in this talk, by the way. I hope that's okay. I'm trying to have more sheep than slides. Okay. So, what kinds of broken symmetries do we talk about? Well, in this sheep crystal, I have broken translational invariance. The sheep aren't just going in any direction. They're actually periodically spaced, and that's they make a periodic lattice of, in this case, sheep. Okay. So that's broken translational invariance. Now, in the case of a ferromagnet, you also have broken translational invariance in the sense that all the atoms and all the electrons are spaced. But what really matters here is that all of the spins are all aligned in one direction. That gives you a broken time reversal symmetry. So that idea of broken symmetry is kind of baked in to what we understand the interactions to actually be in the system between the spins. And similarly, in an antiferromagnet, you've not only broken time reversal symmetry, you've also broken, yet again, another translational symmetry. So the idea of broken symmetry is a central concept in condensed matter physics, and it describes a significant fraction of of how we understand the physics of interacting electrons and materials. Okay. Which brings me to the question of order parameters. So how do we characterize what the broken symmetry in the system is? So we invent, well, sometimes we invent a number that describes what that broken symmetry looks like, but most of the time it's actually like a measurable property. So for example, in a ferromagnet, this is the kind of magnet that you have in a refrigerator, a useful order parameter would be what the total magnetization in the system is, what the dipolar moment of that magnetic material actually looks like. And you could track that, and that would be a measure of how ordered it could be a measure of how ordered your system is. And in the case of an antiferromagnet, it's what we sometimes call the staggered magnetization, which is sometimes measured as the difference between the two magnetizations between the upspins in the system and the downspins in the system. Okay, so how does that vary? How do these order parameters vary? Oh, you might like to hazard a guess. What would you describe as an order parameter for the sheep crystal, by the way? Anyone want this thing that we invented? It's a silly question. There's no such thing as a sheep crystal, so there's no. One thing that you could do for a crystal is measure the distance between the atoms, for example. And that would, and if there's a single distance a single correlated distance that they all converge on, you could watch that evolve, and that would be like your measure of how well ordered the system is. Okay, so what happens as a function of temperature to this order parameter? So I've got an order parameter on the y-axis here, let's call it psi. It's just some way to characterize how well ordered these systems are. And at high temperature, I want this order parameter to be 0. In other words, the system hasn't broken the symmetry, it hasn't ordered. And then at low temperature, I want it to have some transition, which we will call Tc, and then this order parameter will start to grow. That'll be a measure of that broken symmetry coming in, of those interactions becoming relevant. Now, when you see this in the material, this Tc is a measure of the scale of those interactions, the energy scale of those interactions. When your interactions are strong, you can imagine that you start to see this broken symmetry or this ordered state at a very high temperature. But at temperatures higher than that, then that thermal energy is much greater than those interactions, and the system isn't able to order at all, or those spins aren't able to see each other anymore, or those sheep aren't able to order anymore. So In the case of a ferromagnet, this would be magnetization, and what you might see is that you have 0 above its critical temperature, and then that magnetization would grow as you go to lower temperature, and that would be something that you could really measure in a material as you cool it down. And an antiferromagnet would be the staggered magnetization, and whatever it is in our sheet crystal. Okay. The second thing that I want to say about this, apart from broken symmetry, is the idea of rigidity. When things become ordered, one central idea is that whatever that thing is, whether it's spin or whether it's atoms or whether it's orbitals, whatever that variable might be, or whatever that property of the electron might be that's ordering, it becomes stiff in some sense. And what I mean by that is when you have spins that are independent, when they're not interacting, they also move independently of one another. They don't see each other. So when they're moving, thermally or otherwise, they're moving in lots of different directions. But when they're ordered and they all move in harmony. I'm not sure if that's coming out in this video very well. But the idea is that when you knock one of them, it knocks all of them. It's the same idea, for example, when my voice is traveling through the air to your ears, it's traveling at the speed of sound. But if I was transmitting sound through the floor, or through a crystal, or through this table, it's going to travel much faster because now you have collective motion of all the atoms that are stuck together in the table. So in some words, the speed of sound in this table is a measure of the rigidity of the system. The more rigid the system, the faster the speed of sound. You get similar things in magnets as well. In this case, it's spin that is now rigid. So if I was to transport a spin signal, so if I was to inject spin into the system, for example, it would travel much faster across this ferromagnet using the collective motion of all the spins than it would through this gas of spins, which we call a paramagnet. Okay. All right, and the rigidity basically evolves a little bit like the order parameter. You can imagine there's no rigidity of whatever's interacting at high temperature, and then as soon as you start to break that symmetry, that's when the rigidity really sets in. Where am I going with all this? Okay. All right, last thing, third thing, take-home point before we get to some of the deeper things. When you have one of these interacting particles, mostly what they interact with are their neighbors, whoever they see closest. Same with those sheep. They only see who's immediately near them, and they see who's immediately near them. And so great, they're all following each other. But if I was a sheep on the other side, so over here and following my neighbors, they might not be doing exactly the same thing. They might be moving in a slightly different direction, I would follow them. And then they would be following each other and so on, until I would meet the other sheep that started following each other in a different way. When those two ordered states of my crystal meet, it's called a domain boundary. And those two domains are sheep moving in one direction in one domain and another direction in the other. Similar with ferromagnets and antiferromagnets. You have these things called domain boundaries where you can nucleate spins all in one direction in one part, but then a spin in a different part would nucleate spins and perhaps in the opposite direction. And that is a really central concept that comes out from the idea of interacting systems, the order that they form, the broken symmetries that they're associated with, and the rigidity with which they order. Okay. All right, so they are some of the central concepts that I want to tell you about. Now let me show you some real things. Here's a crystal that we made in my lab. It's a ferromagnet. And I've got a little gold square across it because what we're going to do is I'm going to show you what the magnetism looks like in the system at low temperatures. And the way we measure the system, imagine I've got a way to scan what the magnetization is doing locally in the material. The way we did this is actually a technique called magneto-optical Kerr effect. It's basically an optical technique to measure what the magnetization of the system might look like. And you can scan it across the system and see what part of it is spin up and what part of it is spin down. Oh, the colors don't quite come out here, but it's probably good enough. The whitish parts, they're red on my screen, are the spin down electrons, and the bluish parts are the spin up electrons. And so what you're looking at here is exactly what those domains look like in this ferromagnet.
What's the scale?
So this is about a 2 millimeters crystal. Yeah, so this whole thing is about 2 millimeters. Yeah. You can get much higher resolution for these scanning magnetization techniques. Excuse me? Yeah, but that's because you're not really seeing what I'm seeing. It does look like white is more, but it's actually red kind of, this white boundary is quite thick, and then there's red in between that. And the white boundary is where there's basically, zero signal on the scale of the measurement resolution. Okay. So that's what boundaries kind of look like in general for a lot of different systems. I'll show you some other kinds of domain boundaries and other kinds of materials that will become relevant. But one way you can actually get rid of domain boundaries is by breaking a symmetry externally that basically biases the system. If you can find a way of telling the system which direction you want it to go. And in the case of a ferromagnet, the obvious thing is to put it into a magnetic field. A magnetic field basically can flip spins. So if you cool the system in a magnetic field, it tells it everywhere whether you should be up or whether you should be down, whether the sheep should be moving left or whether they should be moving right. And that's, when you cool the system in a field, this is what you see. All of the domain walls have more or less gone, except maybe around a few defects. But the whole system becomes one direction of spin. And that is actually a pretty deep idea. You've got a broken symmetry. In this case, it's time reversal. And what you've put the system in is in a time reversal symmetry breaking field, a magnetic field. In other words, you've externally broken the same symmetry as the order parameter. And by doing that, you've basically coupled directly to that order parameter and told it which direction you want it to go. And this idea is strongly generalizable. As long as if you understand what the broken symmetry is in your system, you can start to guess to how to control it. What kinds of ways you can externally bias the system by putting another symmetry breaking field around it. And I'll give you a couple of examples of that in a second. Okay, so yes, I'm just summarizing what I said before. The magnetic field breaks the same symmetry as the order parameter itself, so they couple together. Okay, and this brings me to the idea of susceptibility. Okay. Let me skip this because the video doesn't come around. Okay. So if you were to point to a part, so this here's, again, sheep flocking, and they're going through a gate. If I was to ask you, where do the sheep look like they're most correlated? In other words, at what point in this picture does it look like they're moving more in the same direction than in other parts of the picture? What part of the picture would you point to? I'm not sure if I phrased my question in the clearest way, by the way. But the basic, but if I was to ask you, where do you see the greatest amount of order, where all of the sheep are pointing in the same direction in this picture?
At the gate.
At the gate. Good. Okay. Why? Because the gate is basically pushing all the sheep together. There's no mystery there, right? The gate is in a way acting like a field on the motion of the sheep. And it's forcing them to be even more parallel than they are when they're away from that gate. In some sense, it's like applying a uniaxial strain on the system. The sheep can either be in this direction or they can be in that direction. But by applying the gate and forcing their motion in one direction, you're basically telling them all through a symmetry breaking field that they all need to move in the same direction. The analogy is not perfect, and I know there's soft-convinced metaphysicists in the audience that might object exactly, but that's the idea. Okay. So, right. So the field is basically telling which direction the system should be biased, which direction it should break symmetry. And that brings me to the idea of fluctuations. Now, on the way to that transition, we know that there is an order parameter, it breaks a symmetry below a certain transition, and above that we want that order parameter to be 0. But it can be 0 in lots of different ways. Like you can imagine that on the way to that point, those particles, those electrons, those sheep are still interacting just more weakly and maybe for a shorter amount of time or over a shorter amount of distance. So I've got again my pixelated image of spin up and spin down, and you have equal probability of being in all directions. What happens is you approach a continuous phase transition, a special kind of phase transition, is that the correlations between, before you break the full symmetry, but and the order parameter is still 0, but before you actually go through that transition to the ordered state, you start to get to see correlations between those local objects. So in other words, you start to get fluctuations, what we call fluctuations, where it really you start to see correlations between spin-ups are more likely to be around spin-ups, and spin-downs are more likely to be around spin-downs. And those correlations become greater and greater and greater until you're at the phase transition. And then you start to have complete correlations between them. So if you're in one place, you're only going to be around spin-ups are only going to be around spin-ups, and spin-downs are only going to be around spin-downs, except, of course, at the domain boundaries. And that's what happens at the transition, and eventually you end up with domain walls. Okay, so how do susceptibilities vary as a function of temperature? That's one of the key properties that we might look for. Well, as I showed you in that in the previous slide, in the previous slide, the correlations, those fluctuations become larger and larger in their spatial extent. The correlations between those spins or correlations between whatever object you're looking at. So you can imagine that the response to that symmetry breaking field is going to become like louder or bigger when you get close to the transition. Okay. So that's so on the left I've got an equation which relates magnetization, the order parameter of a ferromagnet, and I've got its response to an applied magnetic field here represented as B. Chi is basically is what we call the susceptibility. It's the linear response to that magnetic field. And as you're cooling the system in temperature, that linear response, chi, becomes larger and larger and larger until it makes the transition into the ferromagnetic state. Now, we have a theory for describing susceptibilities. And that theory basically tells you that susceptibility is inversely proportional to temperature minus Tc. And that Tc, as I mentioned earlier, is related to is basically a measure of the strength, the energetic strength of your interactions. Okay. All right. Here's another example of a kind of susceptibility and transition that you might look at. Here I've got a picture, a cartoon of a crystal that is what we call orthorhombic. What that means is that the actual repeating cells in this periodic system are actually little rectangles. And they form domain boundaries because the rectangles can be in two different directions. This is an optical image of what those domain boundaries look like. That they form these straight lines, and this is basically the domain walls of rectangles pointing in one direction versus in another. Now you can bias the system to be in one kind of rectangle or another by a symmetry breaking field. But in this direction, it's not a magnetic field like it would be in a ferromagnet. You have to use the broken symmetry of the system itself, like whether it's what direction the rectangle is. And in this case, the symmetry breaking field is simply strain. Just like the sheep going through the constriction, it's like squeezing the crystal in one direction. And so here's a cartoon of those same atoms, and if I squeeze them, these are in a vise, let's say, this is my picture of a vise, I can move that domain wall so then I can get dominant rectangles in one direction and not the other. And if you take that optical image again, as was done by Tanatar back in 2010, you can see that those little stripes, the domain walls, actually all disappear. So it shows you the generality of this idea. You have a broken symmetry. You know what that broken symmetry is. You choose a symmetry breaking field so you can control everything about what that broken how that symmetry is broken in your system, what fraction of it is in one direction or another, and that kind of gives you a control parameter over lots of different materials. And it also gives you, if you're trying to find out what that broken symmetry is, it gives you a probe of it as well. Okay, so now let me take you to quantum critical points. All right, we talked about phase transitions as a function of temperature. There's another kind of phase transition that happens. So here, let me use the laser pointer for this part. So we talked about transitions as a function of temperature, which would happen at some finite value. And what you're looking at here is what's known as a phase diagram. Because I've included some other parameter, a non-thermal parameter that can also tune the nature of that phase transition. This can be, for example, some change in the chemical composition. It can be pressure. It can be magnetic field. It can be any number of things. And that transition can kind of start to go to zero. Now remember, TC is related to the interactions in the system. And so what it's telling you is that that phase transition can happen at zero temperature. So if you could hold your system at zero temperature, you could have a phase transition as a function of that non-thermal parameter, but without temperature even being a part of it. You now have a zero temperature phase transition, but now some critical value of this parameter. What's interesting about this is that it's not just that you have fluctuations in space, like we did in the thermal transitions that we talked about earlier. You actually also have fluctuations in time. And that's because there's no energy scale in the system. You have fluctuations from the Heisenberg uncertainty principle itself. And that's what's kind of neat about studying these kinds of phase transitions at zero temperature. Okay, and why? Why do you have a phase transition at zero temperature? Well, it's because whatever the interaction strength that's connected to the system going to zero temperature is telling you that there's some vanishing scale in the system. Okay, I will come up with some examples in a second. Now, a lot of my career I've spent trying to study the physics of quantum critical points. And the reason why is because there's a lot of material systems that are around these quantum critical points. What you see is superconductivity. In fact, the highest temperature superconductors that we know of, modulo the high pressure hydride superconductors, which, well, let's just leave that subject. It's embarrassing for all of us in Canadian. But a lot of the unconventional superconductors that have the highest temperatures, highest TCs, often have their highest TCs around what appears to be a critical point, some vanishing energy scale in the system. This is controversial. Not everyone believes that this is what's going on, but I think phenomenologically, everyone agrees that this seems to be like a common feature in a lot of these systems. So one of the reasons why I'm interested in this problem is because studying these kinds of phase transitions that have this vanishing interaction scale, you tend to have new kinds of fluctuations and new kinds of physics that emerge that somehow lead to high temperature superconductivity. Okay, what's an example? I showed you before this orthorhombic crystal. This came up in a specific kind of material that I was studying when I was a postdoc called the iron-based superconductors that were discovered in 2008. And it turns out that these seem to be very likely near some kind of critical point, but the whole question for many years was what kind of critical point it was. And it turns out that there are at least like a couple of order parameters that are tied together as a function of temperature, and that's what made the system kind of complicated. One experiment that we did when I was a postdoc with Ian Fisher at Stanford and Junho Chu, who's now a professor in Washington, was that we applied strain on these materials, similar to the strain that I showed you before. We were getting rid of these domain wall boundaries. And you can see that, well, we didn't have quite as good as images as the Tanatar and the Canfield group, but you can see that these domain walls, these dark lines and white lines, would disappear as soon as we applied strain. Now, the reason why we wanted to do that is we wanted to couple to that broken symmetry inside the system and discover what it truly was. And so one of the things that we did more recently is that oops, don't know how I did that, is that once we found a measure of what the internal broken symmetry was, we looked for signatures of it in all sorts of properties, and it looked like they had kind of this quantum critical behavior. In this case, we were measuring a transport property known as the Hall effect as a function of doping and temperature. And if you squint your eyes and you think about that diagram that I showed you in the previous slides, it looks a little bit like there's this quantum critical point on top of a superconducting dome. So it looked like that kind of physics was relevant. I should point out that my good friend and colleague in the audience at the same time was busy proving that there wasn't a quantum critical point in the system. So thanks for that, Professor Dai. But it shows you that this is actually a pretty friendly field, and we all have our ideas about what's going on in the underlying physics, but there's still a lot of open questions. But anyway, what was the broken symmetry? What was the order parameter? Well, we started to thinking about, we knew that the system was orthorhombic and it had this structural anisotropy. We thought this might be driven by an electronic anisotropy, and that's what we call nematicity, like some label that we gave to anisotropic electrons in the system. So you can imagine that the electrons somehow want to have a preferred direction in the system, and maybe that's what was driving all the structural changes, and maybe that's the internal order parameter that was driving the superconductivity. And we characterize this by just the anisotropy and the electrical resistance. That's what this number here means, just the difference between the resistance in the A direction and the resistance in the B direction. That became a proxy for our order parameter, which is basically just the electronic anisotropy in the system. So what do? We strained the systems. Here's on a piezo stack. We looked at how this parameter was responding as a function of temperature. You can see this divergence. This basically shows you that it really looks like a susceptibility that looks 1 over T like, and that diverges right on the critical temperature itself. And other people followed up on this work and mapped this kind of susceptibility as a function of, in this case, doping or sulfur content in these materials. And you can see that they see this color plot basically shows the size of this divergence in the susceptibility. And right near the critical point, namely where that transition goes to 0, where the order parameter disappears, where the interactions driving that broken symmetry disappear, that's somehow where you have the largest response, the largest susceptibility to that external way of breaking that symmetry. And so again, phenomenologically, it looks a little bit like this quantum critical point with some fan represented by the susceptibility around a superconducting dome. Okay, so that's pretty cool. Or at least that's what drove a lot of my research for a while. There was a measurement that we did in these systems when they were superconducting called scanning squid. For those of you who don't know, it's another way to measure the local magnetism in a system, but with very high resolution. You basically have a little magnetometer that goes across the material, and you can measure what the magnetism is. But you can also measure what the superconductivity is doing as well through the same kind of signal, just in the opposite direction. And so we worked with Cam Moeller at Stanford and her postdoc at the time, Bina Kaliski, who's now professor at Bar-Ilan University. And they came up with this image of what the superconductivity looked like. This probably should look familiar by this stage in terms of the other images that I was showing you. They're just the domain walls of the orthorhombic crystal, of the domain walls of this broken symmetry crystal. But what they saw, but she's not measuring structural anisotropy here. She's not measuring anything structural at all. What she's measuring is the superfluid density, right? And what they found is that the superfluid density, in other words, the superconductivity, was much, much higher at the domain wall boundaries than it was anywhere else. So where the system was basically had these defects in the crystal, where two domains kind of met together and had the structural disorder, that is where the superconductivity was the largest. So this was a bit of a surprise, and it's always haunted me. And it's haunted me for this reason. At these domain wall boundaries, that's where the structure changes from one direction to the other. So there's a lot of strain here, right? And we've already been using strain to try and probe the internal broken symmetries of these systems. In other words, the strain was coupling directly to the broken symmetry of the material itself. And now what I'm seeing is that the places where the strain is the largest, at the places at these domain wall boundaries, that somehow is where the superconductivity is the greatest. And remember, never mind. You don't have to remember it. So it got me thinking, is it possible that at the domain wall itself, you're basically tuning the critical point? Maybe the strain is that non-thermal parameter that is tuning you across this phase transition. So maybe I've got a magnet on one side and a magnet on the other, but in between I've created some way to tune across a phase transition. And that's perhaps why I'm tuning across basically that phase diagram across superconductivity. So, and this idea has always haunted me. It happened, we measured this in 2010, and I always wondered whether you could actually have quantum criticality at these domain wall boundaries, even though the system on either side is not quantum critical at all. It was maybe nowhere near a phase transition. So I was always very interested in this idea. Okay, got about 10 minutes or something like that. Yeah, 10, 15 minutes. All right. And I was wondering whether you could use it to do something useful. So I'm going to take you, if this wasn't already like a lot to take in, I'm going to take you on just give you one slide about something completely different. And that completely different thing is a technological problem. How many of you have heard of Moore's Law in this room? Right? I'm sure more of you have heard of Moore's Law than put your hands up. But anyway, the idea is that chip technology is basically increase in capacity or decrease in size by a factor of two every 2 years. So basically, you have this like logarithmic increase in like processor capacity as over time. But we're kind of getting to the physical limits of the technologies that we have. So people in the technology sector are kind of looking for new ways to have memory components and processor components. And so there's one idea out there of using antiferromagnets to basically store information and also process it because it's faster. You can pack components much smaller to kind of keep up with Moore's Law. What has this got to do with anything? Don't worry, I'll bring it home. All right. The way people use antiferromagnets is in the following way. Here you've got a picture of this is actual thin film antiferromagnet, and they've made a little device out of this with 8 contacts. And what they do is that they pulse electrical current in one direction and electrical current in another direction, and they basically measure the resistance. Pulsing along the black direction, you get increases in resistance, electrical resistance. Pulsing in the red direction, you get decreases in electrical resistance. It's basically like a transistor, right? 0 and 1, 0 and 1. You can like switch it. That's the idea. Okay. What does this have to do with anything? Well, it's to do with the mechanism of how this works. How do you go from a low resistance state to a high resistance state? And it's all to do with domain wall boundary motion. So what they're doing when they're applying the current is that you're moving a domain wall boundary, and because the difference in resistance of this domain versus this domain, you go from a low resistance to a high resistance. So all of that physics of these antiferromagnetic components is really about domain wall motion. And I read about this. I wasn't interested in this kind of thing. I think it's a very interesting field, but it wasn't something that was driving my research. But I came across these papers whenever it happened in 2016 or something like that, when the first paper came out. And it got me thinking about this problem that I was working on with the scanning squid. Well, what if you chose a material where the boundaries themselves were very close to a critical transition? Could you make a more effective way of doing the same kind of thing? That's the way I was thinking about it. So, I studied some materials. These are layered transitional metal dichalcogenides. They're made of these lovely layers of niobium sulfide, and they're intercalated with some magnetic element, iron, nickel, whatever you want. Why did I want to study these materials? Well, back in the late 70s, early 80s, Stuart Parkin and Richard Friend were studying these materials. And they were looking at the interaction scale, this transition temperature from the susceptibility. And they looked at it for all the different transition metal, from all the different magnetic elements: vanadium, chromium, manganese, iron, cobalt, nickel. Now, it might not be obvious to you right away, but let's ignore vanadium for a second. But if you look at chromium, these are all positive. If you look at cobalt and nickel, these are all negative. And remember, that TC is connected to the interaction scale, right? So what it means is that the interaction scale driving the magnetism in these systems is going from having a positive value on one side of the transition metals to negative on the other side. And there's only one way you can go from positive to negative values, and that is if you cross zero. If you cross zero, you've got a critical point. So I decided to study these iron compounds, which as you can see kind of vary between their positive and negative, hoping that they might be close to some kind of critical point that I could use in exactly the kind of technology that was being studied for these antiferromagnets. So that's how we came across these materials. Okay, so we used focused iron. We took one of those single crystals. We used focused iron beam to make, this is false color. I hope that's obvious. We used focused iron beam to kind of machine these 8 contact devices with false color. We push current through the blue direction and the red direction. We see very stable, non-volatile switches, and they were like order of magnitude larger than these other systems. And another interesting thing is that it didn't matter how many times you pulse this current along each of the directions, you always got the same resistance. Whereas for the previous systems, it seemed like you were getting like a different resistance each time. Not only that, but the current that we needed to use to get this up and down behavior was like 2 orders of magnitude lower than these other systems, and it was like an order of magnitude faster. So I was patting myself on the back at this stage. I was like, quantum criticality can be relevant for something, right? So I was excited about this idea, but as it turned out, it has nothing to do with quantum criticality. But I'll tell you what it's got to do with. It's not completely unrelated. Here's one thing that we also did. We made a device that looks a little bit like a guitar. And we pulse current in the AB direction, which changes the domain boundaries in this part of the sample. But actually, we could see that signal propagate all the way to 35 microns away from the active area. As far as I know, that's as far as anybody's been able to it's basically a way of switching memory over in that corner over here by having an electrical pulse over here. So it's like non-local switching. So it was like a very powerful, very efficient, very fast way of doing this. I can skip this part. You can look at the critical current as a function of temperature, and it basically looks a lot like an order parameter. So it should remind you of basically the current that you need to actually achieve this varies as a function of temperature very much like the order parameter does. So it tells you that it's coupling to the broken symmetry of the system. Okay, but what about this idea of quantum criticality? Why was this relevant at all? Well, kind of. Okay. We did notice something very unique about the switching characteristics of the system. So here's we changed the amount of iron in the system from 0.31 to 0.35. So a very small change. For those of you who don't do condensed matter physics, you're just like, this is irrelevant, right? This isn't the percent kind of change. Like, why would this make a difference? Well, it actually changed the signal between one kind. So what was a low resistance in this sample was a high resistance in this sample. A high resistance in this one was a low resistance in this one. Like the behavior changed completely in the opposite direction. So this was quite perplexing. But as it turns out, there were 2 different magnetic orders. One of them had stripy antiferromagnetism, and the other one had zigzag antiferromagnetism. And these have 2 different kinds of resistances. And that's why we were getting this opposite behavior. But that small, what it showed you is that these iron compounds were right on the boundary of 2 different kinds of order parameters. So it wasn't quite quantum criticality, but it was at least a similar idea that you're basically between energy scales. Okay, so there's a secondary energy scale, which is the interaction with the next nearest neighbors, and that's basically what's changing as a function of the intercalant in the system. Okay, so it seemed to be useful for something. So just to summarize, I guess if I was to point to any morals, we started with a grain of salt, just a crystalline structure. And all we wanted to learn was what the broken symmetries in the system are, what they couple to, how we could tune them and control them. And then we had this idea, well, maybe we could use, if you're on the boundary of a phase transition, the boundary of some other equilibrium state, could this actually be a way to tune these materials in some very sensitive, very fast way? And from that can we actually prototype it to do something maybe a little bit useful? And even though perhaps what was going on in these materials wasn't actually what I hoped would be going on, it shows you I guess the importance of the creative process, that sometimes it doesn't matter whether your idea is a good idea or even the right idea. What matters is that we have ideas and they lead to other things that are sometimes unexpected. So let me just thank the group, my group that drove a lot of this physics, and particularly Shannon, who did all of this antiferromagnetic switching along with my postdoc at the time of An. And let me just leave you with some more sheep flock. Thank you very much.
Okay, we have time for some questions.
So, with respect to the hello? So with respect, with respect to the superconductor, so the squid is measuring like Meissner locally, I guess? Okay,
that's right.
So it's measuring superfluid stiffness, and that's largest at these domain walls. But I mean, the scale of that image that you showed was huge, like 30 microns.
Right.
So that was an iron superconductor?
That's right. That was the iron superconductor. And the reason why we knew it was the domainable boundaries is because you can also image for the experts in the room, the vortex lattice.
Okay.
And you can see that the vortices stick in a line which is natural at a domainable boundary.
I see. So if you go and do something like SDM, do you actually see a larger amplitude there as well? Or do the coherence peaks? Has anybody done that?
I don't think anyone's done that, right? Yeah, I haven't seen that. It's a good question.
I see.
Yeah.
Okay.
Our scale is way bigger than STM. So STM often just images one domain. I actually haven't seen many STM papers that actually have two domains in them. Yeah. Only Abhay Pasupati had a few on the lithium-ion arsenide, I think.
A completely different question, man. Why does in your last part of your talk, why does a change such a small amount of iron completely change the magnetic structure? Do you have an understanding of that?
Yeah. So it turns out to be a next nearest neighbor interaction, which I glazed over a little bit. And basically, changing the iron intercalation changes the packing of the iron. It just makes those a little bit closer. And we're just talking about like fractions of an angstrom. But that, so the system seems to be an RKKY interaction, which is an oscillatory exchange. And it seems to be that that second nearest neighbor is like right on the boundary between two. So that's our understanding of it.
Other questions? Yes. Oh, there's one online. Okay. Yes. You want to read her question out loud so everyone can, well.
Yeah. Just wondering, let me see what the... Okay, could the change in iron content from 0.31 to 0.35 be due to crossing the superstructure composition at 0.33? Well, we've measured the 1/3, the system that's right on stoichiometry. And what you actually measure there is the coexistence of both those magnetic orders. So I think it's just because there's probably some variation in the strain in the system at that magic value, and some parts go zigzag and some parts go stripy. You get so the 1/3 you get both coexisting in the same system, in the same sample.
James, does the structure do anything funny at the two compositions that reflects this?
Yeah, it's a good question. So we haven't done like X-ray diffraction at those temperatures, unfortunately. But what we have done is a pretty extensive TEM at higher temperature, and the structure doesn't seem to change very much. But it's a good question, what happens at low temperature? We don't know that.
Hi. I have a two-part question. So is it possible to control the distribution of domain walls?
Is it possible to control the
them?
distribution of the...
do they occur randomly in your sample, or is it possible to control their distribution in the crystal?
Of the domain
Oh,
walls.
domain walls, yeah.
Oh, yeah, sure. Like you can control it through, well, it depends what the domain walls of. If they're domain walls of this orthorhombic structure, then you can apply different amounts of strain. And you can, so domain walls generally form around some defect in the system, or maybe some way to minimize the global energy in the system. And what you're doing by applying a strain is that you're adjusting where that minimum kind of lies, right? And the result is that you can tune just how many domain wall boundaries you actually can have in a system just by straining at different amounts.
Okay, thank you. And the second part is, when you're thinking about these domain walls as kind of a local region of quantum criticality, these quantum critical subsystems live in a lower dimension than your original quantum critical point. So
The
imagine
domain
you-
wall boundaries are two-dimensional.
So imagine you are thinking about a layered system like a
Oh, okay.
two-dimensional-
If it's a single layer, sure.
Yeah.
Then they're one-dimensional. Yeah.
Right, usually they live one dimension lower than your actual system, right? The domain walls.
Yes, that's right.
So the quantum critical region is living in a one reduced dimension. So
That's true. Yeah.
So that's not the original quantum criticality that you have in the phase diagram.
That's true. That's very true. That's
So
right.
Is there a systematic way to understand what that means?
That's a great question. I wish someone would study that. Like, I think it's actually a really fascinating question. No, I mean that. I think I didn't get into it, but actually, because of exactly the situation that you're talking about, you're in a reduced dimension at the domain wall boundary, and then you have all of the right kinds of features to be tuned to right on the boundary of that critical point. But as far as I know, no one studied this. But I think it's a very exciting regime that like very few people have kind of got into.
So James,
Chimao is probably about to tell me, no, we studied this 5 years ago, and you were...
no, I'm not going to do that. I was confused by something that I should know. So in the nematic case, the order parameter is discrete, and I can understand the kind of domain walls that's associated with an icing variable. Now, for a ferromagnet, for a magnetic case, I would have thought that the domain walls require some icing anisotropy, and yet these are d-electron systems, and spin orbit should not be all that large. So how do I actually think about these domain walls of the last part of these materials?
They're not ferromagnets, they're all antiferromagnets.
Oh, they're antiferromagnets.
They're antiferromagnets, so they actually break translational
I'm
symmetry.
even more confused in the sense that how do I think about icing variable out of this?
I'm trying to, sorry, let me just, that's not what I want. That's what the domain walls look like. So one of those domains would be just stripy order on the left-hand side. And then there are 3 configurations of the domain walls form. And that's what a domain wall would look like.
But these are magnetic domain walls.
They're also structural domain walls. There's an electronic anisotropy with each of these domains. There has to be a structural response.
But the magnetic order parameter is like a XY magnet, or is like
It's an
icing?
out of plane antiferromagnet.
Okay, so maybe there's some geometrical reasons for it to be for the spin to be pinned in some direction.
Where are you talking about the spin being pinned? You mean around the domain wall?
Yeah.
Or?
Well, maybe we should talk afterwards. I'm just confused by this, something very...
Well, so what these represent here, the dark green line would be spin up and the light line would be spin down. Yeah. And basically it's meeting a domain wall with another stripy region. And this one might be okay, that's going to be in the same direction, but this one's going to be frustrated here because it wants to be a spin down in this direction.
Yeah.
So...
No, I think that's fine, but I think I'm confused if I think in terms of the order parameter that you told us about.
Yeah, okay.
Do you have any understanding of what's mediating the non-local switching?
Yes. So it's actually a bit more trivial than I wanted it to be. So I was hoping, well, okay, so I do think there's some collective motion of the, so I think every time that we're pulsing current, then we could be launching like a magnon that's carrying some spin, but actually it's a more trivial reason than that this actually happens. When we have this device, it's actually stuck with on a substrate with some epoxy, right? Which means that its length is fixed, right? If its length is fixed, imagine I'm pulsing current in this direction, and I mentioned that the structure must be anisotropic. So if I'm pulsing current in this direction and I'm turning this into a single domain, it means that I'm either stretching or shrinking this part right here, right, depending on which way the domain goes. Because I've got, before it was all domains, now it's just one domain, which means I'm stretching it in one direction. Does that make sense? Structurally stretching it, that's right. So if I'm stretching it here, but the whole system has to stay the same length, this part here has to shrink. And when it shrinks, the order parameter goes in the opposite direction. So that's one of the quasi-trivial reasons why we actually saw switching locally. In fact, what was interesting is that the signal here was much larger than the signal right here, the closer contact, and that's because it's closer to the edge of the system. Yeah. So imagine stretching a rubber band. Yeah. Anyway.
Yeah, I have a question. So are there some explanations of the origin of the zigzag order? I know for the stripe order, I mean, large J2 can stabilize this phase, but for the zigzag order, I'm quite confused.
Well, zigzag order is pretty common, I guess, in honeycomb systems, I suppose. So our collaborators, Jeff Neaton, did some pretty extensive density functional theory. I'm not sure if this is an explanation or just a statement, so forgive me if I haven't answered your question, but what they did is that they calculated kind of minimum energy for different magnetic orders. This is what the DFT folks can do. They can calculate stripy and they calculate zigzag. And what they found was that a next nearest neighbor interaction, depending on its value, could make the zigzag a lower energy than the stripy. In other words, the system would go zigzag because of that next nearest neighbor interaction. So the explanation is that it's that next nearest neighbor interaction which is changing as a function of doping, and it's making the system go from stripy to go from zigzag. But that's not really an explanation, because it's just saying that they put in artificially what a magnetic order is, and they calculated that it was a lower energy than another one. So yeah, that's the best I can give you.
So the next nearest order, you mean the J2 Heisenberg interaction?
Yeah, J2, and also an interlayer one as well.
Okay, I see. Yeah. And yeah, I also have a question. So is this material metallic or insulator?
Is this material?
Metallic or insulator?
It's metal.
Oh, I see.
Yeah.
Thanks.
All right, if there are no further questions, let's thank James again.
Thanks.
And there's still some